So nanotechnology, as we know today, plays a large role in shaping the future and the present of medicine. And briefly defined, it is the application and synthesis of materials in the nano level. And today I'll explore the application it has in disease research. And a major contributor to this is just because of the interdisciplinary approach that it has, combining biomedical sciences, material sciences, engineering, and the innovative possibilities with nanotechnology is essentially endless. So today I'll specifically be focusing on nanoparticles and microelectromechanical systems, which are both subsets of nanotechnology. And so before we delve into what nanotechnology is, we'll look at what were the precursors to nanotechnology. So composite materials. So humanity, as we know it, existed for a long time before technology came in to improve our lives. And so composite materials involves the blending of two or more materials. And through our technological ages, we went from copper to stone to bronze to iron. And bronze is a classic example of what composite material is. And composite materials now shifted towards what we consider to be the glass age, as suggested by Corning, which is actually a glass manufacturer. So some examples of composite materials in practice are an F-14 and F-15 fighter jets, which is where they were first introduced, and at this time it was mainly for more simple purposes such as chair design, but then it developed into wing and fuselage design. And one of the classic examples of this is the Boeing 787. It's composed of 50% of composite materials, giving such flexibility and strength in its structure, and followed by only 20% aluminum as well as some other metals. And so, if we skip ahead and look at this slide here, we'll see that the application of composite materials has been an exponential trend since the 1960s, very reminiscent of Moore's Law, suggesting that the application of technology is ever so exponential because it's continuously improving on itself. Similarly, we can see on the figure set right here that in commercial aircraft, the percent of the structural weight made by composite materials also shares that exponential trend. So what is nanotechnology, and why is it that I'm talking about it today? So nanotechnology, as I mentioned earlier, is studying materials in the nano level. So this exists in the 1 to 100 nanometer scale, and it has very diverse applications in biomedical sciences. So very much my focus today will be on cancer, and we can see that when cancer is diagnosed, we can often inject these nanoparticles or other nanomaterials, and this gives many possibilities for treatment, including imaging, localized therapy, as well as killing of the cancer cells. And it's very fascinating, and I hope you're excited as I am. So nanotechnology of solar panels. So this is the reason I would like to discuss this today is just to show the diversity of application of nanotechnology. And traditionally in solar panels, up to 30% of the incident light is lost, mainly due to reflection of this light. However, with nanotechnology, we can subsidize this to only a 10% loss in light. So how this is achieved is by applying a one atom thick layer of magnesium fluoride, and the structure that it's presented as is in nanowires. And so when incident light strikes these nanowires, it refracts the light in towards the solar panels, essentially acting as an extra layer to the solar panels. And so, and these can also be multi-coated. However, the problem is that they can be applied to single-layer solar panels. So to overcome this, we use technology, a physics principle, surface Plasmon resonance, and it's described as a collective longitudinal oscillation of electrons. And so the way that we can use this principle in solar panels is through three possible mechanisms. The first over here describes it as acting as an extra layer on the solar panel, essentially acting as a conducting surface. The second over here suggests that it can trap the energy and it can refract it into the solar panels, with the third saying that it will excite the electrons existing on it will excite the electrons, and these electrons will pass through the current. So now to the more interesting stuff. So to test nanotechnology in vivo, meaning that in the organism, we need to test biocompatibility, which essentially means that we need to test how applicable it will be in vivo, just because we don't want any toxicity effects, or we essentially want to be compatible. So a study was done, and it was using gold nanoparticles, and essentially the gold nanoparticles had different substrates on their surface. So some of these included citrate, biotin, and just a precursor solution of gold chloride. And what we'll find here is that with the citrate and biotin, you'll see that the cell survival is pretty consistent. However, with the precursor, as expected, it declines, right? Because it's very toxic to the cells. And these were incubated in leukemia cells for over 3 days. Thus, the concentration increases over time. However, when we compare one of the other substrates that were on these gold nanoparticles, CTAB, it was very toxic. And when we compared the CTAB with CTBAU, being the two lines over here, we'll see that the cell survival did decline. And so the researchers were interested, is it because of the CTAB that this decline was occurring, or was it purely because of the gold nanoparticles? So what they did is they washed these gold nanoparticles, and then they transfected them again, and you'll see that very much so the gold nanoparticles do not prove to be toxic to the cells. So this suggests about compatibility of these nanoparticles. So with cancer detection, some of the more traditional methods of cancer detection include self-identification, routine mammography, as well as clinical breast exams. However, with cancer, there's so many biomarkers, such as DNA, RNA, and protein, that there's almost endless possibilities for how nanotechnology can prove to have success in cancer detection. And so the one I'll focus on today is, again, gold nanoparticles. So with cancer cells, there's a specific antigen. An antigen is something that the cell expresses. And so the one of these antigens is EGFR, epithelial growth factor receptor. So with gold nanoparticles, what we can do here is we can conjugate something called a Raman reporter. And what Raman reporters do is they're again involved in physics principle called Raman scattering of light. And with Raman scattering, you're able to improve the contrast of the imaging by 200 times brighter, giving giving physicians the ability to clearly see where the cancer exists. And so once we conjugate with Raman reporters, we use a substance called polyethylene glycol. I'll later describe it in my talk, but polyethylene glycol essentially makes it soluble in vivo. And conjugated to polyethylene glycol is the antibody. And so antibodies essentially bind to these antigens. That's how this principle works. So with these GNPs conjugated with Raman reporters, then conjugated with these antibodies, they can essentially bind to these cancer cells that express those biomarkers. And with this, as I mentioned earlier, you're able to improve the contrast by 200 times brighter. And this is very comparable to quantum dots, which is another application of nanoparticles, this being more superior to that in its contrasting capabilities. So with cancer, how do we treat cancer? So some of the more common practices include laser therapy. And the problem with laser therapy, as you can see here, is that it's not very specific, as in it can often also damage neighboring tissue. So it's not as selective. So what are some other options? What we can do is we can do photothermal therapy and photodynamic therapy. And photodynamic therapy essentially has something we called photosensitizers. And with photosensitizers, you apply it on where the cancer exists, and this will excite the photosensitizers, essentially again targeting the tumor. But with the same problem with laser therapy, it does also damage neighboring tissue. So what's another possibility? We have photothermal therapy. How does photothermal therapy work? Well, we essentially have dyes, and these dyes have fluorescent properties. And so when the laser strikes these dyes, they essentially excite electrons, and these electrons, when they come back to the relaxation state, they they target the cancer. And this is more specific than the previous two methods I discussed. However, the problem is that over time, it loses its fluorescent properties, thus not being very viable long term. So, nanoparticles, once again. So nanoparticles can incorporate this principle of photothermal therapy, and this is called, with nanoparticles, gold nanoparticles specifically, plasmonic photothermal therapy, PPTT for short. And essentially how this works is, we have the cancer diagnosis here in this patient. So when we inject these gold nanoparticles, it will first conjugate around the tumor. And when we strike with the laser, how this works is, you excite the electron forms an electron cloud. This electron, within a matter of picoseconds, quickly cools down and exchanges energy with the gold nanoparticle lattice. This gold nanoparticle lattice again cools down, exchanging energy with the environment. And what is that energy? Kinetic energy, which heats the tumor, and it's very specific. And these gold nanoparticles, they don't face the same problem as with conventional photothermal therapy, because they do not lose their properties, and they can be used long term. So this is an example of cancer treatment using nanomaterials. Next, graphene oxide. So graphene oxide is essentially a single atom layer thick of sp2 hybridized carbon. It's a very, very thin sheet. So graphene oxide again has is very biocompatible, and how we make this is we first add oxygen-containing functional groups, and this makes it more soluble in vivo. Then, if you remember from when I was discussing the Raman reporters with gold nanoparticles with the polyethylene glycol, we conjugate the polyethylene glycol over here, and we make a system which is graphene oxide with polyethylene glycol, abbreviated as GoPEG. And as I'll explore later, GoPEG is used in cancer treatment, and it is also used in trapping the cancer cells. So paclitaxel is a chemotherapeutic drug that is used to treat cancers. Paclitaxel is commonly incorporated in a solvent system called Taxol. And the problem with Taxol is that it creates severe toxicological effects as a side effect. So how can we incorporate nanoparticles plus a very useful drug, paclitaxel, and incorporate it in vivo and treat the cancer without those repercussions faced with Taxol? So with paclitaxel, this is the structure that's presented here. It has a hydroxyl group, and this hydroxyl group can be conjugated with graphene oxide. Now, when studied in mice, this first graph over here tests to see what the relative tumor volume over a extended period of time is in the mice. And with GoPEG, graphene oxide, polyethylene glycol, plus and dash PTX, which is paclitaxel, we can see that this subsidizes the relative tumor volume over days the greatest. And then this is followed by Taxol, which is which provides toxicological side effects. And then when compared to the controls, which is just saline solution and just a GoPEG, which we expect not to have any efficacy in cancer treatment, you can see that they have no effects. Similarly, when we look at the survival rate, you'll see a similar trend. With GoPEG PTX, the survival rate is much longer compared to Taxol, with the control groups not having an effect on the survival rate. Now, micro-electromechanical systems. So these are essentially lab-on-a-chip technologies. It's essentially in the 1960s, microfabrication of systems were popularized because of the semiconducting nature of silicon. And so, with this in mind, we can create these chips on the micro level, which have diverse applications in biomedical sciences, in medicine, in engineering, and microfluidics, which is the study of manipulating fluids at the micro level. The number of publications that the number of publications over time since the introductions of MEMS technology, lab-on-chip technologies over the period of time has once again been exponential, just showing how promising these technologies are in their biomedical applications. So with MEMS technology, some of the most common materials that you'll find are silicon dioxide, gold. You'll also find so you'll find these materials, and similarly with nanoparticles, you want to test their biocompatibility. So a simple experiment was designed. So what they did is they had a chip with all these different materials that would normally be incorporated in MEMS technology, and they had an empty drug reservoir just to compare how this whole chip would perform in vivo. And what they did is they had this chip in a cage, and it's just a mesh cage. And similarly, they had a control, and this control was also just an empty mesh cage with no chip inside of it. And so leukocytes, which are the number of white blood cells, are often involved in our immune responses, and with a growing number of leukocytes, that indicates that the system would not be biocompatible, or that there is immunological impacts of these technologies. However, when comparing these substrates which exist on the MEMS chip compared to just an empty cage, you'll see that the total number of leukocytes are not that grow on the substrates are not significant, and this just goes to show how much promise there is for these technologies in vivo, and how much application there is for these technologies. So, as I mentioned earlier, graphene oxide can also be incorporated in MEMS technology. So on this figure over here, you'll see that graphene oxide is pegylated with PEG, and this is then conjugated with EpCAM. And if you remember from the gold nanoparticles where I talked about epithelial growth factor receptors, a similar antigen that expresses on cancer cells is called EpCAM. And so what we can do is we can conjugate EpCAM antibodies onto these graphene oxide. And so what's over here is that there's just a silicon substrate, and on the silicon substrate there are these gold nanoparticles. It's very unique in shape. They're just a flower shape. And what you'll also find is that these graphene oxides, they actually absorb much more strongly to these gold nanoparticles than they do to the actual silicon substrate. And this diagram over here just shows that these EpCAM antibodies essentially trap these these cancer cells which express EpCAM. And when they did an ex vivo experiment flowing human blood, the percent capture rate with these gold PEG chips was 92.1%. Isn't that unbelievable? 92.1% of the cells were captured by these gold PEG chips ex vivo, and it's only a matter of time before we do in vivo experiments with this technology. So another example of MEMS are through this study evaluated MEMS as resonators. So essentially there was a chip, and on this chip they had a 9x9 grid of 81 MEMS resonators. And this is a scanning electron microscopy of what that looks like. And so with tumor cells, you find that they have a difference in stiffness, and this term is described as viscoelasticity. So there's a technology called atomic force microscopy, and what this technology does is it essentially evaluates the stiffness of cells, which can indicate which are the cancer cells. And this graph over here is what atomic force microscopy, AFM for short, looks like. So you'll have the viscoelasticity on this axis, and you'll have the viscosity, and then that's a measure of force. So what occurs is that again, the downside with AFM, however, is that it does not account for them. It does not account for the mass of the cells. So because of this, there's no clear distinguish. It's not very clearly distinguished what are the cancer cells versus the healthy cells. So, however, with MEMS resonators, they're able to capture exactly what these cancer cells are because they're able to account for the mass of these cells. And so I'd like to end my talk on ethics. And so in 2004, there U of T scientists described that there is a gap between nanotechnological scientists versus the general public. However, another commentary suggests that there's actually a new gap, and that is that we're moving towards speculative ethics. We're looking at what if nanotechnology did so and so. What if nanotechnology? Instead of focusing on what are the implications of nanotechnology in the now. So to resolve this, the paper presented that there should be there's two ways to resolve this matter. One is to find common ground between the scientists with the general public and the ethicists, and see what are the most pertinent issues that we can all agree on needs to be discussed. The second would be to distinguish nanotechnology in the now versus nanotechnology in the future. And through these means, ethicists will be able to find a new understanding of what nanotechnology's implications are in the sciences. Thank you.
So, questions?
I have a question.
Yeah.
So, you mentioned the GoPeg PTX,
Yeah.
and you showed the graphs of that. So were those human trials?
Those were rodent trials.
Okay.
It was still in vivo, however.
Okay. So is this something that has gained any ethical approval to move forward?
I'm not too sure about the ethics surrounding the ethics surrounding its application in humans. However, I do see that by using this rodent model, it is very promising to see what holds for humans with this GoPeg technology.
Okay.
Can you go back to the graph about the GoPeg and the paclitaxel for a second?
For sure.
So you mentioned that the top graph is for tumor volume, right?
Yeah.
So, and you also mentioned that Taxol is pretty effective in killing tumors, right?
Yeah.
But you also mentioned the side effect of Taxol is that it's toxic. So why would you think that GoPeg plus paclitaxel is more effective than Taxol in reducing tumor volume in the top graph?
Okay, so interestingly, PEG as well, polyethylene glycol, actually does have toxicological effects. However, when it's conjugated in this system, it requires heavy degradation for it to actually show toxicological effects. However, essentially, my belief is that because Taxol provides these side effects versus GoPeg PTX, which is not, as well as with the fact that we can that these GMPs are that these GMPs are so small, I just see that could be reasons why it shows better efficacy in Taxol.
So, tell us more about speculative ethics. Can you distinguish between a probable future and science fiction that can't possibly be the future? And, I mean, that concept suggests that you can do that the future trajectory is sort of predictable, and so that you would allow differentiation between ethical discussions that surround things that actually will occur in the future as opposed to those that might be in science fiction but will never happen in real life.
So, with that in mind, I think that it is still important to see, it is still important to evaluate what could occur with nanotech. However, without, I think that at the same time, we still need to understand how fast should we move with this nanotechnology, because I mean, as I've shown, like there's just so many trajectories you can take this technology with, that unless we really understand some of the ethics behind that, we can't really look into the what if questions as fast as quickly.
Yeah. But let's take some specific things like gray goo, right? Gray goo is the idea of like nanoparticles that can eat everything made out of carbon and so on, right?
Yeah.
And destroy the earth and all living things thereby. And also the nano-louse. Everybody in this room has seen pictures of this nano-louse, this little tiny machine in amongst red cells in the blood that's doing all this cool stuff. And we're very far from either one of those existing, right? There isn't any gray goo yet. And the nano-louse, which is often the first slide in people's nanotech talks, because it's so beautiful and intriguing, that also we're very, very far from that, right? So I think the idea of speculative ethics would say that we don't need to discuss the ethics of gray goo and the nano-louse, because it's not very probable that we'll have either one of them anytime soon. Whereas there are other things that, like we already have in a primitive form, and it will get better, and so it's a part of the present. So, but don't you think that there could be surprises, and the things that you've excluded could actually happen? Like there could be nanolice, I guess it's the plural of nanolice, and there could be gray goo and you know, the kind of particles in Michael Crichton's prey and all that stuff. So how would you go about defining these categories of the things we should worry about and the things we shouldn't? How would you, if you were in charge of the ethical committee, how would you set about this?
Okay. I think it's first important to evaluate who holds nanotechnology. Like what are the so the scientists progressing with the nanotechnology has to be compared with the regulations that policymakers have towards nanotechnology. Because I think that without regulating where it's going to go, as you mentioned, it could just happen that we might have these other forms that could be more destructive.
Yeah, but isn't it true there are no regulatory bodies in this area at all now? We're just assuming people working in nanotech are so incredibly nice and ethical that everything will be fine. But like, as opposed to medicine, where you know there are all sorts of confining regulations and bodies that have to approve things. In nanotech at the moment, there are not any of those things. And in fact, I think it's important to figure out when do we need regulation, and how do you define the threshold for what is the moment where we say, whoa, stop everything, this needs to be regulated, right? Because do you know of any laws at the moment that regulate nanotech? I don't.
Not that I'm aware of.
No. So it's a completely unregulated technology of great promise that will obviously impact medicine and all other spheres of human endeavor in the long run. So other questions?
I have
Oh, sorry. Oh, okay. Do you see any use of nanotechnology in other areas other than cancer research?
Actually, just some of the things that really stuck out at me are the imaging capabilities of nanotechnology. So even for pathologists such as Dr. Solis, I could see a lot of promise in that field. However, outside of medicine, nanotechnology, it's just due to the nature of how incredibly small it is with its diverse strengths. I could see applications in almost any discipline.
I have a question just because I'm not very familiar with the applications of nanotechnology in vivo. So a lot of the things you were suggesting to treat disease involved injecting these things into someone, right? So do those degrade naturally over time?
Yeah, that was a good question. With nanoparticles, there's actually a study done, and it found that it did accumulate in the stomach and intestine. However, within 1 week, there was almost no trace of it.
Okay.
Yeah, so there is degradation involved in it. Yeah, you have to be carefully optimistic with anything. Yeah.
So other questions?
So if you explain the degradation, right? So
Yeah.
basically this complex that you're talking about isn't toxic because it's like two compounds conjugate together, right? So, but you're saying if in vivo this thing can undergo degradation, don't you think the toxicological effects could come back in later stage in some other organ of the body unintentionally?
Yeah. that very much is a possibility, and I mean that's why, from my understanding, we don't have this in humans yet, right? But yeah, we have to see like how this interacts with other biological aspects in our body, and to make sure that this degradation does not occur.
Yeah, well, I'm gonna send a link to your talk to Robert Burrell to show him how